Well, let's take a look at chapter 6. Chemical calculations. So we're gonna, let's see, up to now we've learned the alphabet. We've learned how to write words in chemistry, form chemical formulas. We learned how to write sentences and balance them, that is, reaction equations. And now we're going to learn what to do with them. And let's just outline this. There we go. Okay, if you need to determine the molar mass of an element, you can read it right off the periodic table. No problem. If you need to determine the molar mass of a compound, you just add up the individual molar masses of the elements. And if there are two or more of them, you have to use that as a multiplier. So in this case, we've got 10,2-fluoride. That's the way we would name it. Type 2 compound. And then we could write the formula from that. So what we need is the molar mass of 10. There's only one of them. Right? So that's why it's 118.71 grams per mole. And then we're going to add 2 fluorines, which should be 19. Okay. Oh, okay. I was looking in the wrong place. 156.71. So what does that mean? Grams per mole of what? Grams per mole of that formula. Okay. So remember, if we have 1 mole of that formula, we have 1 mole of 10, and we have 2 moles of fluorine. All right. What's the formula mass of H2SO4? What is H2SO4? I guess it depends. Right? It starts with hydrogen, so it's pretty sure it's an acid. It can be an acid if it's dissolved in water. Just that formula, we would say what? Hydrogen sulfate. But put it in water, it becomes sulfuric acid. So if we want to find the formula mass of that, now, in this case, the answers are given in atomic mass units. So what we're looking for here is the mass of each of the atoms. Right? So for that formula, we would have 2 atomic mass units of hydrogen. We would have 1 atomic mass unit for sulfur, which I think is 32. 3206. Atomic mass units. That's if we're saying 2 atoms, 1 atom, 4 atoms. And then for the oxygens, right, 16 of those each. All right, so can I estimate that? Let's see, this is 32 plus 2 is 34. And 34 and 64, 90 something. 98. How about that? Atomic mass units for that formula: 2 atoms of hydrogen, 1 atom of sulfur, 4 atoms of oxygen. All right. We haven't talked about the mole yet, have we? I used a unit of measure we haven't even discussed. Okay, here it goes. Those numbers that we see in the upper right-hand corner of these little squares would be the weighted average for all the isotopes of that element in terms of atomic mass units. Up to this point, that's all we know. But that doesn't help us any, not for actually working in the lab, because we measure things by mass or volume. So in this case, mass would be the best choice. And our balances aren't set up for masses in atomic mass units. They're set up for grams. So what we need is a unit that gives us enough atoms or enough molecules of a compound that we can measure it in grams on our balance. And that unit is the mole. Hey, when you get your breath, come sign in. So when we say a mole of things, it's just a number. That is, it's actually derived from a physical characteristic. But as far as you're concerned, the mole is just a number. 1 mole equals 6.022 times 10 to the 23rd things. It could be atoms. It could be ions. It could be molecules. It could be formula units. Right? For an ionic compound, it wouldn't be a molecule. It would be a formula unit. By definition, this is the number of carbon-12 atoms. That isotope of carbon, that's the number of these atoms that it takes to make 12 grams. Okay? So if we have exactly 12 grams of that isotope, we know we have exactly that many atoms of this isotope. Now that's the definition. It's not going to do us much good. And I always round it off to 3 decimal places. The reason for that is over time, the values are refined, become more accurate, but they're only accurate at about the 7th or 8th decimal place. So if we round it up to 3, then we can use that from now on. All right, how many eggs does 1 mole of egg contain? 6.02 times 10 to the 23rd. That's how many eggs. Which came first, the chicken or the egg? Right? It could be that many chickens if they all hatch. Okay, so now that we have that value, what that allows us to do is to weigh an element, weigh a compound, and convert that to a number of atoms, molecules, whatever the case may be. So now we have that bridge between the atomic mass units and grams. An atomic mass unit would be for just 1 atom, say, of carbon-12. Be 12 atomic mass units for 1 carbon atom. But if we have 12 grams, now we have a mole of carbon atoms. And to find the number, and the number is exactly the same as the one that says atomic mass units. It's also grams per mole. So it's on this periodic chart, it's in the upper left-hand corner. So the molar mass of nitrogen, you look that up, it's rounded off to 2 decimal places, is 14.01. Molar mass of carbon dioxide would be 12.01 for carbon, and then 2 times 16 for the oxygens, you have 44.01 grams per mole. And if we weigh that many grams of carbon dioxide, it's kind of difficult because it's a gas, but it can be done. If you have that many grams of carbon dioxide, you have exactly 1 mole. Now, eventually, I'm going to show you why that's important. not just because you can weigh it. But when we start doing calculations and we have so much reactant, mass of reactant, we want to find out how much mass of product we have. You can't go from mass to mass in a balanced chemical equation because the equation is based upon numbers. So you need to convert that mass into numbers, then you can move to another place. That's coming. All right. So how about, and notice also, remember when you have an equivalence, 1 mole, that's abbreviation for mole. You just drop the E. 1 mole equals this many, 2 times 10 to the 23rd. Let's say for our purposes, molecule. When you have an equivalence, you can make a conversion factor out of it, right? Move this one over here in the denominator, it's equal to 1. Move this one over the denominator, it's equal to 1. So for this problem, what's the mass in grams of 2.5 moles of C2H6, which is ethane? We can use, we got moles here, we want grams there, so right, grams goes on the top, moles on the bottom. And this is 6.022 times 10 to the 23rd per gram. And all we have to do is divide that into this value, and we get 75, excuse me. No, I'm sorry. Are you writing in pencil? I was barking up the wrong tree. Right? We want to go from moles to grams. So 1 mole of that compound equals how many grams? 2 times 12.01 for carbon and 6 times 1.01 for hydrogen. So that's, let's see, 24.02 and 6.06, 8, 0, 30.08. Now our conversion factor. 30.08 grams per mole. Then let's see. Now, why is there's 07? 0.01, 2, 606. Mine's right and there's wrong. 75 grams, roughly. We canceled the moles, left us with grams. How about the number of moles in 50 grams of water? Now we'll go the other direction. Say 50 grams of water. Let's see, 50.0 grams of water. We need to cancel the grams. Leaves us with moles. Okay, so what's the magic number here? Water, 2 times 1.01 for hydrogens, and then 16 for that 1 oxygen. That's 18.02 grams per mole. Grams are on the bottom though, 18.02 here. So 18.02 divided into 50 would give us 2.78 moles of water. So if we have that many grams of pure water, we have this many moles. All right. about aspirin. Aspirin's been around a long time. I mean, it was here before the turn of the 20th century. C9H8O4. You know what its chemical name is? Not that you need to know, but I'm just curious. It's called acetyl salicylic acid. Actually, anytime you go to the drugstore and look at pain relievers like Aspirin, those things, lots of them will have salicylates in them. And they're cousins of aspirin. In fact, aspirin is acetylated salicylic acid because that way it goes into your stomach and the acids remove that acetyl group. And when they do, it continues to pass on through your stomach, and that's what goes into your bloodstream and gives you pain relief. And let's see, what's the proper term for a fever reducer? Antipyretic, I think it's called. Okay, so if we have 1 mole of aspirin, 1 mole of aspirin, question is mass of 1 mole. Oh, okay, we just want to calculate 9 times 12.01 for carbon, and 8 times 1.01 for hydrogen, and 4 times 16 for oxygen, and just add them together. Should be 180 grams. Okay. All right. So we've learned how to write chemical formulas. And even if I've said so before, it bears repeating. The subscripts in a chemical formula give the number of atoms of each of the elements in that formula, in one formula unit. So in our example, 1 molecule of a dinitrogen tetroxide has 2 nitrogen atoms and 4 oxygen atoms. That's what we see. If we could get down small enough and actually see the molecule, that's what we would see. That's the microscopic view. The macroscopic view is what we actually work with in the lab. And that's the connection between the atomic mass units and the molar mass. How much does a mole weigh in grams? So at the macroscopic level, if we have 1 mole of those molecules, that means we have 2 moles of nitrogen and 4 moles of oxygen. How many moles of carbon atoms and hydrogen atoms are present in the 2.5 mole sample of C2H6? Okay, this is what I was getting at before, I think. 2.5 moles. 2.5 moles of C2H6. And it wants to know moles of carbon and moles of hydrogen. Oh, that's too easy. So if this is how many moles of carbon atoms are in 1 mole of that formula, then 2.5 moles would be 2 times that, wouldn't it? So we have 5 moles of carbon and 15 moles of hydrogen. The ratio should be 2 to 6 or 1 to 3. 1 to 3. Just checking myself. All right. Oh, we're back to aspirin again. Let's see, how many moles of carbon atoms, hydrogen atoms, oxygen atoms? Okay. Molecular formula. Oh. If you just have that 1 mole of that formula, then you're going to have 9, 8, and 4. Right? It's that simple. Okay. I don't know why I keep this slide in here. I think some students like these flow charts. I just prefer dimensional analysis, and that gets me where I want to go without having to memorize all these movements. So it's there if you want to look at it. All right. Oh, there's my approach. Conversion factors do it for us. Given, you know what your target is, you know what's given, you have a conversion factor that will change units for you. Okay. So have we done this one before? How much will it cost to drive from Beckley to Atlanta? No? Okay. That's a dimensional analysis problem. What do you need to know if you're going from Beckley or wherever you're from? Beckley to Atlanta, Georgia. How much is it going to cost? That's the question. Well, we need to know how far is it, right? Distance. All right. So that would tell us how many miles we're going to drive. All right. What else do we need to know? How much gas does it take for each of those miles? Like mileage, vehicle mileage. That's the way you spell it, I think.
Yes.
And then once you know how many gallons it's going to be required, then you can go to how much does a gallon of gas cost? All right, so the fuel cost. Fuel cost per gallon. All right, I passed, let's see, a little wide spot in the road called Jesse on the other side of Oceana. $3.09 a gallon. That's the cheapest one I saw on my way from Beckley to here. Now back in off the other locations, it might be cheaper, but it might cost me the difference in the price just to go get it. And it's cheaper than it is at Sam's in Beckley. That's $3.30 up there. So I'm gonna fill up on the way home.
Drive all the way out to Illinois, you can get it for like $2.75.
I don't doubt it. Yeah.
I mean, it's 500 miles that way, but.
And whenever I drive to Atlanta to visit relatives, as soon as I cross the West Virginia border into Wytheville, I stop and get gas because it's 25 cents cheaper there. Okay, so if we know the distance in miles, let's see, did I work it out down here? 385 miles is about how far I drive from my house to my relative's house. Okay, we want to convert that to gallons of gas. So we need miles on the bottom and gallons on the top. All right, well, let's see, what did I pick for this one? 25? Yeah, 25 miles per gallon. If you got a 4-cylinder car, you might get better than that. Mine's a 6-cylinder, so that's about as good as I can hope for. Right? That gets rid of miles and leaves us with gallons. Now we have gallons, and we have how much does it cost a gallon? Let me see what it was when I put this slide together.
That's 280.
280. Okay. That's been a while ago. $2.80 per gallon. So that cancels gallons, and that leaves us with how much it costs to go one way. Okay. $43. It was back then. All right. So if I want to get back, I better double that. And if I'm going to do any driving around, which is inevitable in Atlanta, it takes you're lucky if you can get anywhere in 20 minutes. Usually it takes 40 minutes or an hour. That's why my relatives live in the suburbs. Driving around money. So I usually pad my total, $86. I'll pad it, maybe go to 100. And that should be enough. Okay, so that's dimensional analysis. We know where we are, we know where we want to go, and we find the conversion factors to get there. Which is closest to the average mass of one atom of copper? I guess I'll leave this in here just to have a good laugh. Right? Are there any copper atoms that are going to weigh 60 or 50 grams? I don't think so. That would be a massive atom. So the answer is going to be E. But how do we calculate it? One atom of copper, one atom of copper. What's the bridge between numbers and mass? It's molar mass of copper. So we need to find out how many moles that is. 6.022 times 10 to the 23rd atoms per mole. That gets rid of atoms, and it's going to be a fraction. Right? It's a fraction of a mole. And now we can go from moles to grams. All we need is the conversion factor for copper, which is 63.55, I think. Get a reflection off that thing. Yeah, 63.55. Okay. And that will give you the mass of one atom. There it is. So this one is kind of a trick question. Calculate the number of copper atoms in 63.55 grams of copper. That's one mole. So it has to be 6.022 times 10 to the 23rd. Right? By definition. All right, let's compare these three: magnesium, zinc, and silver. Magnesium, zinc, and silver. And we've got 100-gram sample of each one. 100 grams of each sample. Which sample contains the greatest number of atoms? They're all the same mass, but each atom has a different mass. Which one's going to give you more atoms? The lightest one, because it takes more of them to make 100 grams. That's all we have to do is just check out our values. Let's say 24, 30, 31 for magnesium, 24.31 grams per mole. Zinc is, I need the periodic table up here where I can see it. I bet there's one in the review document. Oh, that's not it. Here it is. Yeah. Either that or you can tell me. 65.39 for zinc. Grams per mole. And silver's a lot bigger. 107.87. Okay. So this one weighs the least per mole. You could go ahead and convert 100 grams into moles and compare those values if you wanted to. But all we have to do is say the lightest one is going to take more atoms to make 100 grams. So magnesium would be the answer. All right. It's just logic. Okay, now rank the following for descending number of atoms. So the most to the middle to the last, the least number. 107.9 grams of silver. 107.9 grams of silver. Zinc, 70 grams. Okay. And magnesium, 21 grams. All right, now we're not 100 grams anymore. We're different masses for each one. So I would look at these in terms of, are there any of them that are exactly a mole? This one. Silver is 1 mole, isn't it? Right, close enough. How about this one? That's greater than a mole. That's equal to a mole. That one's greater than a mole, and 21 is less than a mole. So if we rank them in order of descending number of atoms, the greatest number would be zinc, greatest number in this example. Then the next would be exactly a mole, and the last would be less than a mole. Okay. Zinc, silver, magnesium. I actually calculated it out here, but you don't have to. If you've only got 3, you can compare them fairly easily. So that should be B, let's see, zinc, silver, magnesium. Yep. All right. Get more and more complicated as we go. I think for the next one, I'm going to have to use Henry Ford. Set up an assembly line. 100-gram sample of each of the following compounds. Descending order of number of oxygen atoms. All right, so let's put them up here. What do we have? We got water, laughing gas, C3H6O2. I think that's propionic acid. CO2. One of those fatty acids we all have in our bodies. Okay, we've got 100-gram sample of each. And we're going to convert to the number of oxygen atoms. Okay. Starting my assembly line here. We can calculate the number of moles of the compounds fairly easily. What we need is the molar mass of each one to go in this conversion factor. That'll give us the moles of the compound. Right? When it says number of oxygen atoms, if we're only going to put them in order, do we have to go all the way to the number of atoms? No, we can go to a counting number. The mole will do it. But first, we're going to get so many grams per mole of each compound. And that'll give us the mole of the compound. Right. This is the compound. All right, so water, we did that one earlier. That's 18.02. N2O. Right, that's 16 for oxygen, and 2 times 14 is 28.02, right, for nitrogen. 4402. Okay. How about propionic acid? Let's see, we need 3 times 12.01 for carbon. We need 6 times 1.01 for hydrogen. And we need 2 times 16 for oxygen. Okay. Where's I pull my calculator out here. Unless you want to beat me to it. No, nobody wants to. You got it? Okay. Okay, I got my number. What's yours? 909. Yep. And that's grams per mole. So this would be 74.09 grams per mole. And carbon dioxide, that would be 12.01 plus 32. 01 Okay, so this will give us moles of the compound. For every mole of the compound, we have 1 mole of oxygen here, 1 mole of oxygen there, 2 moles of oxygen there, and 2 there. So rather than calculate the moles of the compound and introduce rounding error and then try to calculate the oxygen, we're just going to do the whole thing at once. Okay, for this one, we need the ratio of the number of oxygen atoms per molecule. So this is going to be moles of oxygen. Per mole of compound, right? Compound. Per mole of compound. That cancels the mole of compound. What's the ratio? Well, this one is 1 to 1. For every mole of water, we have 1 mole of oxygen. Naphthalene gas is the same way. Propionic acid is 2 moles of oxygen for every mole of compound. And carbon dioxide is also 2. Now we can do the calculation. Right? Just take 100, divide by 18.02, and times 1, 5.55, I get. Yeah, moles of oxygen in 100 grams of water. Next one is 2.27 moles of oxygen. And then our fatty acid times 2. 2.70.
How are you doing?
I'm saying 100 divided by this number times that number. Yeah. And when you've got nothing but multiply and divide, it doesn't matter what order they are. You can say that times that times that divided by that divided by that. Or you can say that divided by that times that divided by that times that. It doesn't matter. As far as your calculator is concerned, you come up with the same answer. And then the last one, 144.01 times 2 is 4.54. So this is my Henry Ford method. I set up an assembly line. I do the same calculation over and over. I just change these parts in here. Well, for Henry Ford, you could have any color you want as long as it's black. But we can change our colors in here. Okay, so they wanted us to put them in descending order. So the most would be this one, right? That would be the most. And then this one would be the next. And this is 3 and this is 4. Okay. All right. Oh, they're the calculations. Okay. So far, so good. Yep. Oops. Off by 100th. Must be a rounding error. Yeah. 44.0 and I had 44.01. All right. So water's first, carbon dioxide second, propionic acid, and then laughing gas. Okay. Doing on time. Okay. Now, the formula of aspirin, calculate the number of molecules in 0.325 gram tablet of aspirin. Why did we pick 0.325 grams? Have you ever looked on a bottle of full strength aspirin? Not the baby aspirin that I take every morning as a blood thinner. 0.325 grams is 325 milligrams. And that's the strength of full strength aspirin. So that's where that number came from. But rather than give you milligrams and have to convert that to grams before we can do anything with it, we just say 0.325 grams of aspirin. And we want to convert that to, let's see, number of molecules of aspirin. Okay. So we can go from grams to moles. That's the bridge from mass to numbers. And then we can do numbers to molecules with, I didn't give this a name, did I? That's Avogadro's number. He didn't invent it. It was his theories that allowed the calculation of it. So we'll give him credit for it. Just slapped his name on it. Okay. 984. C9H8O4. I don't remember what our value was. Do you? I could flip back and find it, I guess. Rather than calculate it again. Let's see. Aspirin. There it is. 180 grams. Oop, 180.2. Let's use that one. It'll come out better. 180.2 grams. And that's 1 mole. So grams cancel, moles cancel. We're left with molecules. And if we calculate it correctly, it should be 1.09 times 10 to the 21. Molecules. Of acetylsalicylic molecules in a full strength tab of aspirin. Have you ever noticed with an older bottle of aspirin, when you open it up, what do you smell? Don't remember? Okay. Nobody sniffs aspirin anymore. It smells like vinegar. Right. The molecule has, let's see, it's a benzene ring like that. And then it has, let's see, acetyl salicylic. Salicylic is COOH, and then no CH2CH. Acetyl. Oops, that's not right. I think that's it. And what happens over time is this part of it right here breaks off. And that gives you acetic acid. That's what you smell. It's not very stable. In fact, when I teach organic chemistry, we make it in the lab just as an exercise. And then we take fat, lard, or some oil and saponify it. Right? Hit it with sodium hydroxide and break it up and make soap. Right? Now, if you got any old timers in your family that still make their own soap, do the same thing. Strong lye, sodium hydroxide, and lard. They usually use lard. It makes soap. In fact, several years ago. I think it was here. Was it here? No, I was teaching organic chemistry over Lewisburg. And one of my students, as a hobby, made soap. And they brought some. He brought some of it to us. It had colors in it, put coloring in it, put fragrances in it. It was pretty nice. The thing about making soap that way is if you got any leftover sodium hydroxide in there, right, the lye, right, it's a very strong irritant. Right? You just put that on your body and ooh, it'll bring the rose out in your skin. I guess that's why Granny Clampett, when she washed Ellie Mae's hair in lye soap, she used rainwater to clean it because that's distilled and it's more effective at extracting water-soluble compounds. That's enough of that. Okay. So when we write this chemical equation, which we have learned to balance, right? We did that already, didn't we? Okay, good. When we write the chemical equation, we have, of course, the reactants on the left and the products on the right. And for this example, we have calcium sulfide plus water yields calcium oxide plus hydrogen sulfide. So that reaction is going to stink because hydrogen sulfide is a gas. And, well, all you have to do is just drive through Greenbrier, close enough to one of their springs, and you'll smell hydrogen sulfide. Or drive past the, I forget who runs that paper mill over there, east of Lewisburg. I can't remember the company, but you'll smell it from the freeway. One of the products there is hydrogen sulfide. They hit paper with, they hit wood pulp with sulfuric acid. And that breaks down the lignin fibers. And they can separate the cellulose from the lignin, and cellulose makes better paper. So they make the paper out of that. And then the sulfuric acid combines with the lignin to make a sulfonated compound. Plus, there's some byproducts that the hydrogen sulfide gets emitted. And that's what you smell when you cross their pathway. Anyway, so is this a balanced equation? Well, let's see. There's one calcium. All right, see that? One sulfur on either side. Let's see, two hydrogens, yep, and one oxygen. So that one's balanced, as written. And when we have a balanced equation like that, calcium sulfide plus water yields calcium oxide plus hydrogen sulfide. Oops. About to write water again. When we have a balanced equation like that, we can look at it two different ways. Either it's one molecule of calcium sulfide plus one molecule of water yields one molecule of calcium oxide plus one molecule of hydrogen sulfide, or you can look at it in terms of moles. 1 mole of calcium sulfide and 1 mole of water combine to make 1 mole of calcium oxide and 1 mole of hydrogen sulfide. That's the way we're going to use it. Because we have a conversion between moles and mass now. These coefficients, of course, the coefficients in front, if there's a compound written here with no number in front, it's 1, right? If you write that symbol there, it's got to be at least one of them. So we don't write the 1. It's 1, 1, 1, and 1. And that's what the coefficients mean. They mean numbers. They mean moles of. But we do reactions in terms of mass. So what we need is to, are you sure we balanced equations already? Yeah, I think we did. I showed you how to balance with my budget method, balancing equations. Maybe I'm thinking of a different class.
Pretty sure we worked on it,
Okay, no, I don't think we have. I better go through it again, just in case. Okay, so this equation we know is balanced because it has the same number of elements, atoms of elements on either side, or moles of elements on either side. So the first thing you do when you're writing a chemical equation and you're on your way to balancing it, and by the way, if it's not balanced, you can't do anything with it, is you write the compounds correctly or the elements correctly, right? If it says react hydrogen gas with oxygen gas and yield water, liquid, that will never balance. It won't be proper, let me put it that way, unless these are diatomic. Remember the diatomic elements: hydrogen, oxygen, nitrogen. Well, let me put them in order: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomic elements. Right? And in that first periodic table I gave you, they had had blue backgrounds. Those are the diatomics. Okay. So this is not balanced the way it is. Right? We need two oxygens. Right? So we use a coefficient. Once you write the elements of the compounds in your equation, you can't change the subscripts. They're chiseled in stone. So the only way you can balance it is with coefficients. So if we have 1 mole of water, that's not enough. That's only 1 mole of oxygen. We need 2 moles. So 2 here. Now that we have 4 moles of hydrogen, we need a 2 there. That gives us 4. Okay. That's weird. I guess I get confused teaching several courses. Okay, the name of the compounds. No, we haven't balanced equations yet. All right. So once you write the elements and compounds correctly, then most chemistry textbooks, at least historically speaking, would say then you balance the equation by inspection, which means nothing. It's just that the writers of the book didn't want to take the time to show you how to do it. So I got a method for doing it. I call it my budget method. And I've got these rules here, and helpful hints. Let's see, did I hand out helpful hints? Yeah, there's this document right here. And there's that one. That's helpful hints. We're going to use those as I show you how to balance various equations. But they're listed here for posterity. You know, they're recorded while we're sharing these files. And I'm just going to leave them on there long enough to get a good recording and then move on and use these hints, these tricks, if you will, to balance equations. All right, now, this one is a little more advanced. So let me pick one. Let me pick a different one. Let's see. How about what if we want to burn methane, right? Natural gas, right? You've got maybe your house is heated by natural gas, or you cook with natural gas, or whatever, or maybe propane. Rather use propane. Who uses propane? Okay, I got one vote. Propane is C3H8. Okay, and when we react it, it's going to be a gas, and we're going to add oxygen from the air, right? And it's always going to make, if the combustion is complete, it's always going to make carbon dioxide and water. Okay, so we've written our compounds correctly. That's propane, oxygen in the air, carbon dioxide product, water product. Now we want to balance it. So my budget method says, first thing you do is inventory your elements. So we have carbon, and I'll put the elements down this side. We have carbon, we have hydrogen, and we have oxygen. That's it. That's all the elements in this reaction. And then for this side, I just count up the number. So we have 3 carbons, we have 8 hydrogens, and we have 2 oxygens. Now you can look at that in terms of atoms, 2 atoms of oxygen, 8 atoms of hydrogen, 3 atoms of carbon. For balancing purposes, it doesn't matter. All right, on this side, we only have 1 carbon, and we have 2 hydrogens, and we have 3 oxygens. Okay, and then sometimes I add them up, like that's 13, right? So 3 is 11, 12, 13, that's good. And this is 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I've counted all the atoms. But you can tell instantly that it's not balanced. You got 3 to 1, you got 8 to 2, and 2 to 3. Those numbers should be the same on both sides if it's going to be balanced. Okay? First trick. If you've got an element on either side of the equation, save it for last. Because when you put a coefficient in front of that, it only changes that element. Right? If you do it early on, then you have to go back and change it again. Because when you put a coefficient in front of these, it's going to change more than one element. And that sets you up to have to go somewhere else and change another one. So we save this one to last. All right, so where do you start? Well, some reactions, you sort of develop an intuition about where would be the most efficient place to start. But if you don't know, right, if you're just beginning, just start at the top. We need 3 carbons on that side, right? So we use a coefficient of 3. Okay? 3 carbons. And that changes the oxygens from 3 to 2, 6, 7. Okay. Now the carbons are balanced. Hydrogens. We're going to go to hydrogens next. So we got 8 hydrogens on this side. We need 8 on that side. So if we put a 4 there, that gives us 8 hydrogens. But now it gives us 4 plus 6 is 10, right? Let's see. 6, 4, yeah, 10. It gives us 10 oxygens. So if I put a 5 here, yeah, that would be 10. Let me see if that's right. 3 and 3. 8 hydrogens, 8 hydrogens. 10 oxygens. 6 plus 4 is 10. Yeah, that's right. Okay. And now you can see instantly that you're balanced. Okay. There'll be other hints coming along. The next one is, I've set it up here with animations. Ammonium phosphate plus calcium chloride yields calcium phosphate plus ammonium chloride. And you can check yourself to see if they're written correctly. Ammonium has a +1 charge. Phosphate has a -3, so you need 3 ammoniums. Those are polyatomic ions, so ammonium has to have a parentheses with a subscript, right? Because the charge on a polyatomic is distributed over the entire thing. You can't change the subscripts of a polyatomic. So that's why we need a parentheses and then how many of them. So ammonia taken 3 times plus phosphate, and then calcium is a 2+, chloride is a halogen, there's -1, so you need 2 chlorines, right? And you do the same thing with the rest of them to get them balanced. Now, if they're written correctly, we do our tally. And notice that if you've got a polyatomic on the left-hand side and the right-hand side, and it didn't break apart in the process, you can use it as a balancing group. That saves you a lot of headaches. You don't have to count individual atoms with those. So we got ammonium over here, we got ammonium over here, and no nitrogens in between. Phosphate, same way, we've got phosphate there, phosphate there. So we're going to use those as our balancing groups. And we've done our initial tally, right? 3 on the left, 3 ammonia, on the right, 1 ammonia. Phosphate's 1 on the left, 2 on the right, calcium's 1 on the left, 3 on the right, chlorine is 2 on the left and 1 on the right. So where do we start? Well, I think for this purpose, I started with calcium. We got 3 calcium on the right. I need a 3 in front of the calcium chloride. Right? And that little red number says this is the order of operation. That's the first step I did. So once we get them all up there, you can't tell where you started if I don't tell you where we did start. Right? So we started with 1. And that changed the amount, the number of calciums and chlorines. And calciums are balanced. Now the chlorines are off. So let's go over on the product side and put a 3, let's see, no, a 6 in front of the ammonium chloride. And that'll give us 6 chlorines, and it'll also change the ammonias to 6. So now we go back to the left-hand side, and we need 6 ammonias on the left, so that's a coefficient of 2. And we're balanced. Okay. So that was trick number 2. Trick number 1 is hold out the single elements to last. Trick 2 is balance with polyatomic ions if they don't change from one side to the other. Right? Some reactions will rip them apart, right? And then you're stuck with going with individual elements. And the other rule is what we try to do is balance with the smallest whole number ratio of coefficients. So while the ratio is established at balancing with, in this case, 2, 5, 2, and 1 as your coefficients, right? You could double those and say 4, 10, 2, and 2, 4, 10, 4, and 2. Right, so that's the only one in that group, I think. Yeah, that's the only one. But that's the simplest whole number ratio. So check your balancing, your coefficients at the end, and be sure that it's the simplest whole number. Can you divide through by a 2 or by a 3 or by a 4 and get a simpler ratio? If not, then you're good with the coefficients that you have. Okay, which of the following is true concerning balanced equations? There may be more than one true. The number of molecules is conserved. No, sorry, it don't work. It's the number of atoms that are conserved. Atoms are neither created nor destroyed, right? And that leads us to Lavoisier's law of conservation of mass, right? The mass of reactants equals the mass of products. And the reason it's that way is because John Dalton said, you can't destroy atoms, you can't create atoms, you just rearrange them. Right? That's the only true one in that bunch. So this would have been a simple balancing, so that's why I'm stopping here with C would be coefficients ratios of 2, 1, 1, and 1. B would be 4, 2, 2, and 2, which would be technically correct, but it's not the simplest whole number ratio because you can divide that whole equation through by 2. Once you get the ratio established, coefficients ratio established, then you can look for reducing the values to the smallest whole number. Okay. This balanced equation says that for 4 molecules actually 4 atoms of iron react with 3 molecules of oxygen to produce 2 molecules of Fe2O3. That's what that says. It also says that 4 moles, let's see, does that say it? Yeah, it also says 4 moles of iron produce 2 moles of Fe2O3, or 3 moles of oxygen produce 2 moles of Fe2O3 in that reaction. So what we're saying is these coefficients give us conversion factors. So if we say, let me write that formula up there again. If we have this one and oxygen, which is 3 and 2, 3, and then 2, oops, why did that? Fe2O3. What we're saying is that if we have, say, 8 moles of iron go into this reaction, we want to know how many moles of oxygen will it take to consume all of that iron. All we have to do is convert moles of iron to moles of oxygen. And the ratio is 4 here and 3 there. Right? So that comes out to 6 moles of O2. So if we have 8 moles of iron, it's going to take 6 moles of O2. These ratios can be used as conversion factors. You can go anywhere in the equation as long as you're in moles. All right. Okay, let's balance this equation. We're going to burn ethane, C2H6, yep, plus oxygen, yields carbon dioxide and water. Okay, so we'll tally our carbon, hydrogen, oxygen. We have 2 carbons, 6 and 2 there. We have 1 carbon here, and 2 hydrogens, and 3 oxygens. Okay, so we're going to hold oxygen till last. It's an element. And might as well start at the top. 2 carbons, okay? 2 carbons, that changes for 5 oxygens. Okay, now we do hydrogens. We have 6 hydrogens here. We need a 3 in front of this one to give us 6 hydrogens. Now it says 3 plus 4 is 7, right? Is that correct? Yep. Now, look, we kind of painted ourselves into a corner because we need 7 oxygens on this side. How do you make 7 out of 2? Right. That's 2 prime numbers, and never the twain shall meet. So we're going to use another trick that's in that useful information. We're going to balance with a fraction. If I say 7 halves of O2 gives me 7 oxygen atoms. Do you believe me? Oxygen's like this. That's an oxygen molecule. Okay? If I have 7 of them, one, two, three, four, 5, 6, 7. I'm going to leave out the electrons. I've got 7 of them, but I really only want half of those. I want 7 halves, right? I just go 1, 2, 3, 4, 5, 6, 7. There we go. 7 oxygens. Okay. Did I lose anybody? Are we finished? I'm trying for the simplest whole number ratio. So you can use a fraction as an intermediate step. to balance the equation. And now we know it's balanced, 762, 762. That ratio is established. So using math rules, if we do something to both sides of the equation, say we multiply it by a number, multiply this side by a number, something times that, times that, times that, times that, the ratio is still the same. Right? The ratio is established now, it's fixed. So I want to get rid of that half. Multiply the whole thing through by 2. All the coefficients by 2. That will put a 2 here. That will get rid of that fraction, right? 2 times a half is 1, and 1 times 7 is 7. And this is 4. This is 6. So the simplest whole number ratio is 2, 7, 4, and 6. Okay? So that looks to me like D. Think you can do that? Yeah, you can do that. A little practice. A lot of these hydrocarbons are like that, like octane in your gas tank. When you burn it, it'll come out. You'll need to use the fraction trick if you want to do the octane thing. Come on. There we go. All right. Stoichiometric calculations. I mean, we mentioned stoichiometry before, didn't we? There's one slide at the end of one of our chapters. Stoichiometry relates the masses of reactants and products. Or, well, in the beginning, it's masses. Right? You can go further with it, but we're going to stick with masses. What it does is allows you to determine, if you know what's going into a reaction, you can tell what comes out with values that you can measure. Or if you want to know how much reactant do I need to guarantee an output of a certain amount of product, you can do that too. Right, and there's your flow chart again. All right, this exercise is a little complicated, so I'm going to try to break it down into, make it really simple. Break it down into steps. Remember, complex problems can be solved, but sometimes you have to break them down into simpler steps. And then once you get answers to the steps, bring them back together. That's what we're going to do here. Okay. The exercise says methane reacts with oxygen and air to produce carbon dioxide and water. We did that one before. Ammonia can also react with oxygen in the air to produce nitrogen monoxide and water. First, we want to do is balance the equations. Then we're going to do something with them. All right, so that's the simple part. We're going to balance the equations. And let's see, methane plus oxygen yields carbon dioxide plus water. Let's see. Do you remember what so we don't have to go through that again. Oh, I did, that wasn't on a slide, was it? Okay. Let's see if I can do this one. Let's see. Carbon, hydrogen. 2 of these. That yields 2, 3, 4. 2 here. That'd be 1 carbon, 4 hydrogens. Nope, that's not right. I didn't count it right. Oh, that is right. That's right. Try that again. Carbon, carbon, 4 hydrogens, and 4 oxygens. 2 and 2 is 4. There we go. That's balanced. Right. Some of these are simple enough you don't have to set up a budget. We are going to do a budget with ammonia. Let's take ammonia plus oxygen yields nitrogen monoxide plus water, correct? Yeah. Most of the reactions you have to balance will give you both reactants and products because the product output depends on reaction conditions. We could change the reaction conditions and come out with maybe nitrogen dioxide instead. But in this case, under the conditions that we've established for this reaction, it gives us nitrogen monoxide. Okay, so let's do our tally, our initial inventory. All right, we have one nitrogen here, one there. Hydrogens, 3 here, and 2 there, and 2 oxygens here, and 2 oxygens there. So we're going to hold this oxygen out for last. And since nitrogens are already equal, we're going to go to hydrogen. So we want to get, how do you balance 3 on this side and 2 on that side? Yes, that's the other trick. Cross multiply. Hydrogen is in one place here and one place here with a subscript of 2 there and 3 there. We put that subscript over here, this subscript over there. That gives you 6. That's 6 hydrogens. Then we have to balance the rest of it. 3 plus 1 is 4 oxygens. And then, let's see, 2 nitrogens. Now we got to go over here and say 2 nitrogens. That changes the oxygens. 2 plus 3 is 5. So far, so good. Now, we want to get 5 oxygens out of that. How are we going to do that? Just like that. Okay, now we get rid of the fraction by multiplying by 2. So that makes this one 4. That makes that one 5. This one's 4. This one's 6. Okay. So let's see. Now we got it balanced. Let's change this to 4. Kind of clean it up because we got to do more with it. 5. This is going to be 4. This would be 6. Okay. All right. Now we got those 2 balanced equations. Let's see if they agree with the slide. 4, 5, 4, and 6. 4, 5, 4, 6. Yep. Okay. Next, what we want to do is say, if we burn 1 gram of methane in excess oxygen, there's plenty of oxygen. It will never run out. So all of this methane is going to be consumed and produce carbon dioxide and water. What we want to know is how much ammonia, what mass of ammonia would give us exactly the same amount of water. This is going to produce a certain amount of water. We want to know how much of ammonia will give us exactly the same mass of water. Okay? So in order to do that, first we have to find out how much water would this produce. And the way you do that is stoichiometry. If you've got mass here, if you've got anything but moles in a reactant or a product, you can't move. It's like there's a great wall here. A great wall of China. You can't get over it, you can't get under it. Unless you're moles. And it's like magic, the wall disappears. So we want to convert this to moles. Okay, let me move that so I can write it in here. Convert methane to moles by using the molar mass. So that would be what? 12.01 plus 4.04, right? Or how? 506, 1605. So that'll tell us how many moles of methane we start with. And I get 6.23 times 10 to the minus 2 moles of methane. Right? Now I want to convert that. How many moles of water would that be? Would that produce? This many moles of methane will produce a certain number of moles of water, and the conversion factor is the coefficients. We're going to take this one, moles of methane on the bottom, moles of water on the top, so that these will cancel. And the ratio is 2 waters for every 1 methane. So I just need to multiply 2 times that number. 1 point, let's see, I'm going to use standard notation, 0.1246. 0.1246 moles of water would be produced from that reaction. Okay? The question then is, if we produce exactly the same amount of water here, how many grams of methane would be required? With excess oxygen here also. So if this is the same number of moles of water, 0.1246 moles of water, and I'm going to go backwards. So moles of water cancel here and leaves us with moles of ammonia, right? So these will cancel. And this is, what's the ratio? Well, for every 6 moles of water, we get 4 moles of ammonia. So 4 times that value divided by 6. And I get 8.31 times 10 to the minus 2. 8.31 times 10 to the minus 2 moles of ammonia. Okay? So far, so good? Or am I scrambling your brains? Now we just need to convert moles to grams. Right? So, all right, we know how to do that. This is in the numerator. This would be in the denominator. Grams on top would be the value we want. So what's the molar mass of methane, ammonia? 14.01 for nitrogen, right? When you calculate the molar mass, you don't use the coefficient. It's just the formula. And then 3.03 for all the hydrogens. 1704. Multiplied times that value. And I get 1.42. So what we're saying is 1.42 grams of ammonia burned in oxygen will give you exactly the same amount of water as 1 gram of methane burned in water, in air, in oxygen. All right. So here's the animated version. We go. Close enough. Rounded off to 3 significant figures. Then we take that one, convert it to moles of ammonia, and then moles of ammonia to mass 1.42. Okay, that's stoichiometry. All right, I think we're coming down to the wire here with yield, percent yield. Let's see, am I gonna need that anymore? Let me look ahead. No. Okay. Okay. What is percent yield? Percent yield is really simple. Percent yield of a chemical equation is you focus on one of the products and it's equal to the mass let me change that. The actual mass of a product divided by the theoretical mass of that same product. Since it's percent, it's times 100. So if we had taken that value of water, 0.125 mole of water, and converted it back to mass, that would be 100% the theoretical product. If we actually conduct the reaction and recover the water from the reaction, and it turns out to be less than that, which it usually does, then you would take that mass and put it over the theoretical mass times 100, and that would be your percent yield. Okay? It always happens. Every reaction, you never get 100% back. Sometimes you get more than 100% back, which means you've got contamination somewhere. But usually, for our purposes, we're going to be less than 100%. So, the theoretical yield for this reaction, and for our purpose, it doesn't matter what the reaction is. If the theoretical is 5.6 grams, and the actual that we recovered from the reaction of that product is 4.5 grams. That would be the percent yield. And let's see, that's
It's like
80 something? 80? Yeah. 80 is closest there. Okay. Oh, we got 2 concept questions. That means we're at the tail end. All right. Pennies produced prior to 1982 were composed of 95% copper. What are they now? They're copper-clad zinc. So that in historical terms, that's called debasing the currency. You're actually removing the intrinsic value of your currency. And the reason the government did it was because to make a penny, it costs more than a penny. You have the value of the copper in a penny is more than the value of the penny as currency. So that's why they dumbed it down. They did that with all silver coins too, about the same time. Okay, on average, these pennies weigh 3.11 grams. So 3.11 grams per penny. Okay, we're working with 95% copper. How many atoms of copper were present in one pre-1982 penny? All right. So if that's the mass of the penny, and we need the amount of copper Right. So the copper is going to be 0.95 copper for every 1 penny. Right. That's a fractional equivalent to percent, 0.95. We'll cancel pennies, and this gives us, actually, that's confusing. Let's do it a different way. That's the mass of the penny. This is the mass of the copper in the penny. There we go. That's better. Uh, 2.955. 2.955 grams of copper in that penny. Okay, so now we can convert it. Let's see, what was the question? How many atoms? So first we need the number of moles, right? Our bridge is grams and moles. Copper was what? 6355. Yeah, 6355. Right, that's moles of copper. Then we can take the moles. This is a chain conversion. And 6.022 times 10 to the 23rd atoms per mole. And that cancels copper, grams of copper, moles, there we go. And that should come out to save us time. There we go. 2.8 times 10 to the 22nd atoms. Actually, this is 3 significant figures. What happened? I chopped one off. Oh. Uh, 6.022. 0. There we go. Just threw away a decimal. Okay. That was concept 1, concept 2, and we'll be done with this chapter. 2-liter bottle of carbonated soda. Let's see, how am I doing on time? 10:30. 10:55. Okay, we got time to do this one. A 2-liter bottle of carbonated soda has an equivalent average 0.2 grams of glucose per 100 milliliters. Glucose is metabolized in the human body by this equation to produce carbon dioxide and water. Use the following steps and the associated equations to determine number of grams of carbon dioxide produced after the consumption of 10 2-liter bottles. So we're starting off with 10 2-liter bottles, which would be what? 20 liters, wouldn't it? 20 liters. Okay. Let's see. Oh, we only need to know, they've already told us how much glucose is in there, right? With 10 bottles. And then each bottle has 0.2 grams per 100 milliliters. We do need to know that. I'm sorry. Yeah, we do need to know that. 20 liters. 20 liters total. How many milliliters is that? Right. We need to know milliliters because the value of glucose is in grams per milliliter. So for every 100 milliliters, we have 0.2 grams of glucose. There we go. So that cancels milliliters and leaves us with grams of glucose. Okay. Let's put that equation up here because it's not balanced yet. C6H12O6 plus oxygen yields carbon dioxide plus water. So we need to balance that one. Carbon, hydrogen, oxygen. 6 carbons here, 1 there. We have 12 hydrogens here and 2 there. And oxygen, 6, 7, 8. 8 oxygens here and 3 here. Okay, so we'll start with carbon. 6 carbons. That gives us 12, 13 oxygens. Okay, hydrogen. We need 12 hydrogens on this side. 6 will give us 12 hydrogens. That's 6 and 12 is 18. Okay, oxygens. And then we've got 6 oxygens here already. If we put a, let's see, 6 from 18 is 12, right? So if we put a 6 here, that'll give us 12 plus 6 is 18. So now we're balanced. Okay. This tells us how many grams of glucose have been consumed. So that would go in this term right here. Uh, 20 liters and 1,000 times divided by 100 times 0.2. So I get 40. 40 grams of glucose. That's where we start with this reaction, this stoichiometry. And we want to know grams of carbon dioxide. Okay, so remember, you can't go anywhere in this equation unless you're moles. So we've got to convert that many grams of glucose to moles. So we need the molar mass of glucose. 6 times 12.01, 12 times 1.01, and 6 times 16. It's a big molecule. And then 6 times 16. Don't trust my ability to do that one in my head. 180.18. 180.18 grams per mole. Divide that into 40. And I get 0.222 grams. This is glucose. So we're going to convert that to, oh, excuse me. Y'all going to let me get away with that. Grams have already canceled. This is moles. Moles of glucose. Now we need a conversion factor to convert from glucose to CO2, and that's 6 here and 1 there. So I get 1.332 moles. It's better with me. Moles of CO2, and we're going to convert that into grams. We just need the value. That's 12.01 and 32 for oxygen. Oops. Try that again. 4401. There we go. Times 1 point. Let's see. There we go. That's right. 58. How about that? 0.6 grams. So there's a balanced equation. That's what's given. convert that to, well, we did it all in one swoop. 59, okay, rounded off to two places, 59 grams. Okay. That's stoichiometry. And that should be the last slide. Yep.